All right. Here we go. Number 12. A student does 60 joules of work pushing a 3-kilogram box up the full length of a ramp that is 5 meters long. What is the magnitude of the force applied to the box to do this work? All right. So, 60 joules of work. It's a 3-kilogram box, so that's work. This is mass. This is distance, delta x. We're looking for the force. All right, so work equals force times distance, which is change in energy. Now they gave you the mass, but you don't actually need it for this problem. So 60 joules equals force times 5 meters. Divide by 5, divide by 5. The force is 12 newtons, choice D. All right, this is an interesting one here. 55-kilogram diver falls freely from a diving platform that's 3 meters above the surface. All right, so they dive. They start off 3 meters. And we want to know what's going on when they're 1 meter off the ground, which is here. All right, what are her gravitational potential energy and kinetic energy with respect to the water's surface? All right, so let's figure out her potential energy with respect to the surface here first, when she's at 1 meter height. Let's see what we get. So PE at 1 meter is going to be 55 kilograms times about 10 times the height, which is about 1 meter. So that's about 550 joules, which if you use 9.8 for 10, you get closer to 540. So her potential energy with respect to the ground right here is 540 joules. This is the only one that could possibly be right. Her kinetic energy is 1080. Let me show you why that is. So let's make this 9.8, make this 540. So her kinetic energy is going to be whatever potential energy she lost. So let's figure out the potential energy at the top here. So PEG equals MGH 55 times 9.8 times 3. 55 times 9.8 times 3, it's about 1617 or 1620 joules at the top, right? So our PEG at the top is 1620 joules. Her P at the bottom is 540, so 1620 minus 540 tells us how much kinetic energy she has, and that's 1080. So it is choice A. All right, a 40-kilogram student runs up a staircase to a floor that's 5 meters higher than her starting point in 7 seconds. What's the student's power output? All right, power is equal to change in energy over time, delta E over T. Change in energy in this case is change in gravitational potential energy, change in PEG over the time. All right, so our change in potential energy is MGH, 40 kilograms, times about 10 newtons per kilogram, times the height of about 5 meters is the height she went, in 7 seconds. So 40 times 10 times 5 is 2,000. Divided by 7 is about 286. Okay, so a little bit lower. So let me do a little bit lower. It's going to be A. If I use 9.8. So in these questions, they're using 9.8. Sometimes they use 10, sometimes they use 9.8. It's usually when it says approximately that they've used 10 for G. 280 watts. What is the magnitude of electric field intensity at a point where a proton experiences electrostatic force of magnitude 2.3 times 10 to the 25th newtons? All right, so this one I gave a point for. This one and one of the friction ones, I gave everybody the point. Electric field. Go to the back here. The electric force on an object is equal to its charge times whatever the electric field strength is. So the electric force on an object is equal to the object's charge times however strong the electric field is. So if you know the force acting and you know the charge because it's a proton, you can figure out the electric field strength. So if electric field strength is the electric force that's being applied divided by the charge of the object. Now, the electric force is 2.3 times 10 to the negative 25th newtons. The charge here is the charge of a proton, which is 1.6 times 10 to the minus 19th coulombs. All right, so 2.3 times 10 to the negative 25th divided by 1.6 times 10 to the minus 19th is, look at that, 0.000001. So it's 1, 2, 3, 4, 5, 6. 1.4 times 10 to the negative 6 newtons per coulomb. So that's that. So charge of proton and electron is given to you on an equation sheet. It's right here. 1e equals 1.6 times. So an electron is positive, or electron is negative, proton is positive. All right, and the last couple questions here, a couple short answer questions. Momentum and energy and a static electricity one. So 1,000 kilogram empty cart moving at a speed of 6 meters per second is about to collide with a stationary loaded cart having a total mass of 5,000 kilograms. After the collision, the carts lock and move together. Assume friction is negligible. Calculate the total combined speed. All right, so before the collision, and then after, right, it's worth drawing this. Afterwards, they lock together, right? And they move as one cart afterwards. One cart with a mass of 6,000 kilograms. So we're looking for that velocity of them stuck together moving away. So P before equals P after. So 1,000 kilograms times positive 6.0 meters per second. This one's momentum is 0, right? Equals the final momentum, which is going to be them stuck together, 6,000 kilograms, times the unknown velocity v. So 6,000 equals 6,000 times v. So divide by 6,000, divide by 6,000. V equals 1 meter per second. All right, so part B asks for the kinetic energy of the combined carts after the collision. So that's Ke equals 1/2 mv squared. So it's 1/2 of 6,000 kilograms times 1 meter per second squared. Show all work, including substitution with units, is important there. So you really want to write the equations you're using, and then you do need to plug in with the variables and their units when you solve it, at least once. You don't need to carry the units all the way through the solution. Some people like to, but anyways, it comes out to be 1 squared is 1 times 6,000, half that, 3,000 joules, the kinetic energy. All right, a lightweight sphere hangs by an insulating thread. Student wishes to determine if the sphere is neutral or electrostatically charged. Okay, so we get a sphere, we don't know what's going on. She has a negatively charged hard rubber rod. Okay, so a negatively charged rod, I'll just draw it in here. Or a positively charged glass rod. Okay, so either or, right? She does not touch the sphere with the rods, but runs tests by bringing them near the sphere one at a time. All right, describe the test result that would prove that the sphere in the given situation is positive. So positive, it can either attract to negative or repel from positive, and. But the problem is, attracting to the negative, that doesn't really mean anything, because if this is neutral, it'll attract to the negative as well. So that never is a good answer, right? You can only determine the charge of something if you see it repel from something. All right? If it attracts, that doesn't, you can't tell if it's charged or not. Until you see it repel, you don't know if it's charged. Because remember, neutral objects, what can happen is they can get polarized, right? I could have, this thing could be neutral, right? And it would get polarized, meaning, you know, the electrons would get drawn to this side of it, and the object's still neutral, but it's polarized. So it would get, you know, pretend this one's not here for a minute, right? It would get attracted towards the positive rod, all right? So it's not charged though, it's just polarized. So it has to repel. If it repel from positive or repel, you probably should say from the glass rod. That's probably what you should say to make it repel from positive, repel from the glass rod. Then you'll know it's charged positively. All right, I'm going to upload these right now and post them, and we'll be good.